Good day and welcome back to part 4 of our discussion on differentiating trig functions. In our previous videos we've introduced the differentiation formulas for the 6 trig functions as well as several new limit type laws, and we've began working through some examples. And we will continue doing so in this video. So without any further ado, our first question or example is, what are the values of x where the graph of the function x plus 2 cosine x will have a horizontal tangent line? And the first thing we need to do to answer this question is to kind of translate it into a mathematical equation that we can work with. So when we're asking where will the tangent line be horizontal, this is just a fancy way of asking us, can you sit up and solve the equation f prime of x equals 0? So we are forcing you to go through that thought process of realizing a horizontal tangent line is a line with slope 0, and the slope of the tangent line comes from the derivative. So a few steps. The first step is to find f prime. So if f of x is a function x plus 2 cosine x, then f prime of x will be 1 plus 2 times the derivative of cosine. And this is one of our new formulas, and remember when we differentiate one of the code trig functions, that's when we have a negative sign involved. And what we would like to know is, where is this derivative equal to 0? So the question mark is indicating let's solve for x. So if we add 2 sine x to both sides, we would have 1 equals 2 sine x. And if we divide by 2, we're really asking, where is sine of x equal to 1/2? Let me draw a simple picture to go with this. So oftentimes when we're thinking about values of trig functions, in particular sine and cosine, we might want to remember the unit circle. Now remember, on the unit circle, and I'm going to pick a point down here, every point can be represented in this form: cosine theta, sine theta, where theta is the angle formed coming from the positive x-axis going in that counterclockwise direction. And in calculus, we will always measure angles in radians unless otherwise specified. So if we want to know where is sine of x equal to 1/2, sine corresponds to the y-coordinate of a point on the unit circle. So what we need to do is just draw in the horizontal line, y equals 1/2. And at whatever points this intersects the unit circle, and note there's 2 of them, but by the periodicity of the sine function there's going to be a whole bunch more, but there's 2 of them that we see, and what we have to know is, for these 2 points, what would that corresponding angle be coming from the positive x-axis going in that counterclockwise direction. So call those angles theta 1 and theta 2. And note there's a common value where sine is equal to 1/2. That happens at pi over 6. And note my picture's not precisely to scale, but hopefully that it gives you the general idea. So the first value would be pi over 6, which corresponds to theta 1. And then by symmetry, we can determine what that theta 2 value would be, because note this corresponding angle in the second quadrant would be theta 1. So theta 2 is going to be pi minus pi over 6, which is 5 pi over 6. So we're just using a few key techniques and ideas from pre-calculus. So x is pi over 6 or 5 pi over 6. But remember, when you're talking about the trig functions, there are many other possibilities where sine can equal to 1/2. And since the period of cosine is 2 pi, it's really a 2n pi that we need to add on to each of these. And I always think we should also specify in here, with n being a whole number, just so there's no confusion. And I also just want to comment that we have to be very careful to make sure that we answer whatever question is asked. Here we're simply asked to find the values of x, and we have found those. But note another reasonable question would have been to ask you what are the corresponding points on the curve. So if x is pi over 6 plus 2 and pi, just for fun, let's write down those corresponding points. So the point on the curve, or I should say points plural on the curve, would be made up of the form an input pi over 6 plus 2 and pi, and then whatever we get from the function as an output when we plug in that point. So as usual, make sure to read the question and answer whatever has been asked. So moving on, let's look at two common examples that involve calculating some limits. And what I'd like to do is just give you a quick reminder and introduce a new version of the formula. A limit that we introduced in our first video on this topic is that the limit as x approaches 0 of sine x over x is equal to 1. And it turns out that there's another version of this that we could state. So think of this as maybe kind of a new limit law that we can use as needed, and we will several times in the next couple minutes. And that is the limit as x approaches 0 of sine of some constant x over constant x is equal to 1 when c, as long as it's not 0, is a constant. So we are going to make use of this new limit law. So looking at the example that we have, the limit as x approaches 0 of sine of 3x over x. If I want to apply this new limit law, what do we need to add into or modify this function we are calculating the limit of? And hopefully what you're noting is it's missing that 3 in the bottom. If we could put a 3 in the bottom, then we would have sine of 3x over 3x, and it would precisely fit the form that we have above. But remember, we can't just divide by 3. That changes the function that we are calculating the limit of. But what we can do is always multiply by 1. So note, all we've done is we've multiplied by 1. That does not change the value of the limit. And if we pull this extra 3 from the top out front, we're left with 3 times the limit as x approaches 0 of sine of 3x over 3x, which is 3 times 1 from our new limit law, and we end up with a 3. And that is a common technique. Let's go ahead and use this same idea again to see if we can evaluate the limit as x approaches 0 of sine of 7x over sine of 3x. And what I want you to think about for a moment is, how do we have to modify this function to get back to the point where we can use this new limit law? Maybe what's a fancy way that we can multiply by 1? And hopefully what you're observing is you have the sine of 7x, the sine of 3x, but if we want to get it back into this form, what we are really missing is having that x in the denominator. So what we're going to do is we're just going to go ahead and put that x in the denominator. I'm going to multiply by 1 as 1 over x divided by 1 over x. And then going ahead and multiplying that 1 over x through the top and the bottom, we would have the limit as x approaches 0, and in the top we would have sine of 7x divided by x, and in the bottom we have sine of 3x divided by x. And note, as usual, we can't simply plug in x equals 0, but we are almost in that key position to use this property above. So what I'm going to do is two things at once. I'm going to take the limit in the top and the bottom, And then just like we did in our previous example, we're going to add in some constants to match up with that formula. So this would be the limit as x approaches 0 of sine 7x over x divided by the limit as x approaches 0 of sine of 3x over x. And then we're just going to multiply the top and the bottom by 1. We're going to multiply the top by 7 over 7. And in the bottom, we're going to multiply by 3 over 3. And we're going to pull the 7 out of the top and a 3 out of the bottom. And when we do that, what we will end up with is 7 times the limit as x approaches 0 of sine of 7x over 7x, and that's a limit we can evaluate. And in the bottom, we have another limit we can evaluate. The limit as x approaches 0 of sine of 3x over 3x. And using our new property above, which we have a star by, so by that property star, the limit in the top is 1, the limit in the bottom is 1, so the overall value of our limit is 7/3. And let me just finish with a quick reminder to make sure that you're using good, proper mathematical notation. So in a problem like this, we're writing our equals at each step. We organize vertically. If we run out of space, we go up to another column. And we're writing those limits at each step as well until we have evaluated them. And if you're in doubt in terms of should I show a step or not, usually students err on the side of showing too little opposed to too much. So do not hesitate to reach out with questions. Stay tuned and take care.